Today we'll be continuing topics in Chapter 3. In particular, we'll be dealing with some practical methods we can use in order to avoid intersymbol interference, and we'll be discussing topics in Section 3.3 and 3.4 of the Sklar textbook. So let's start first with some observations about the matched filter. So this is a typical communication system. And we have the transmitting signal, which has a certain pulse shape. And what we can do to represent the pulse shape is to have a pulse shaping filter at the transmitter. And we model at the input to this pulse shaping filter some impulses. So this is the data here. For instance, this could be binary data with logical ones, two logical ones followed by logical 0. And the impulse response of the transmitting filter will give the shape of the signal. So if we think of this as h, t, x, t being that means that the shape of this pulse would be, just this, the transmit impulse response. So when we want to say we're going to put have a certain shape for our pulse, whether it's a square wave or whatever shape it is, we can say it's generated by this transmitting filter. Then we have another filter which represents the channel. So that's what's going on here. And we also modeled the channel as being introducing noise. Then at the receiver, of course, this is our linear sampling receiver. And so we have a filter here, which we've learned should be a matched filter. So this is a typical model for a communications system. And if we look up at the corner there, we think that the matched filter should be matched to what is received. And of course, now what is received is actually the transmitted pulse, which is acted on by the channel. And so if we look in the frequency domain, that would be the product of those two frequency responses. So when we match, we're essentially matching both the transmitter and the channel. That's what would actually maximize the signal to noise ratio. We also typically would use a sort of an equivalent model for this system. We could, in a completely linear channel, just completely combine all three of these filters into one effective, so sort of the equivalent effective filter. And of course, that response is just the product of all three. So that's a nice model. Makes it a little easier to understand what's going on. I will give you one caveat, though, is to be careful with this noise, because there is a difference between these two noises. This one here has got like infinite bandwidth. It is the ideal additive white Gaussian noise. And of course, that Gaussian noise with infinite power is going to be filtered here, so that when it comes into the decision statistic, the contribution of noise has some reasonable power. And when we're adding here, we have to be careful that we don't add the infinite bandwidth noise, because there's no filter following this noise, but it would be the equivalent amount of filtered noise. So I mention this just because if you're going to do some Matlab simulations, it's important to realize that when you decide to lump together all your filters here, you have to be careful that your noise is the equivalent filtered noise. So we had the discussion previously about the matched filter. And again, what the receiver sees is a combination of both the transmit and the channel, which is why the received filter should match. You match not to just the transmit, but to the transmit plus the channel. And the channel, however, may be unknown. For instance, we may be using a system which already has transmitter and receiver filters set, and we don't know what the channel is going to be. And we want a general solution. So sometimes we don't even discuss the channel, and what we say is you're matching it to the transmitter. So it depends on how you're looking at the problem. It's kind of like, in this case, we're assuming that everything is perfect, that we have essentially an all-pass channel. Because what does an all-pass channel mean? Well, an all-pass channel would mean that this HC would just be equal to 1. And so we would have that we would just have the transmit and the receive. Okay, so I just want to clarify that. It's mentioned in the textbook, and so in different parts of your experience, you may see where the channel is included, like when we're doing equalizers. Of course, channels can be very important. We're going to include it. But for the discussion that we're going to have today, we're really concentrating on this idea of received transmit filter for shaping, received filter which is matched to that. And for this discussion, we're not going to see the effect of the channel. In fact, we're just going to assume that the channel is this perfect all-pass channel that does not affect the system. So now, of course, what signal waveform do we want to use? That's what we're discussing today. So we're looking at some practical choices of what would be good signal waveforms. So if we look at the theory says any waveform will work. All are equivalent, but that's because we sort of assume that the channel doesn't, like crush the signal. It's an all-pass signal, and so then it wouldn't matter. Now, in practical systems, you have many imperfections that come into play. For instance, the components themselves could be imperfect, and the channels could also be crushing. I say crush the signal, but the channel could also introduce intersymbol interference. And so because of these practical limitations, we're going to look at, instead of any waveform, we're going to look at some waveforms that would be good in this situation. I'll just mention one example of imperfect component. Imperfect components, that could refer to the bandwidth of the components. Maybe they're limited in bandwidth. When we say the channel is crushing the signal, it's because we're using some component that doesn't have much bandwidth. Or it could be, for instance, the timing recovery. Timing recovery is needed. We have like this idea of a sampling oscilloscope, a sampling receiver, and a sampling receiver needs to have timing. It needs to know when to sample. What's the ideal time to sample? And because of that, that's another imperfection that can come into the system. So these are the kinds of concerns that makes us want to look to what would be practical choices. And in theory, we have any choice. So let's choose some choices that will be robust to these practical impairments. So essentially what we're discussing today is how we can try to avoid intersymbol interference by using these practical choices. Remember, just a quick recall of what is intersymbol interference. Remember, the channels are always band limited. That's physical. I'm going to pass my signal through a coaxial cable. The coaxial cable has a certain passband that can be supported. Channels are always, sorry, not channels, signals are always time limited. And if signals are time limited, we have a problem, because if they're time limited, that means they have infinite bandwidth. And therefore, we're trying to pass something with infinite bandwidth through something that's band limited. So that means we're always going to have some sort of cutting on our signal. I said it won't crush it. If it crushes it, that means we have a whole lot of cutting of the signal. But in any case, when it is cut, if it is band limited, that means it's going to lead to stretching of the pulse. And because of this stretching of the pulse, we're going to get overlapping of pulses. The current pulse is going to be overlapped by previous pulses. So again, this is all a matter of degree. If we have an extremely wideband a channel which is much wider than the bandwidth of the signal, this effect will be negligible. However, if we're in a situation where we're trying to send our signal through a very constrained bandwidth, then this is a very real problem. And this is just an illustration to show what we mean by intersymbol interference. It starts off as a nice limited in time pulse, but because of going through a band limited channel, it gets spread out in time. So it's no longer rectangular, it exceeds. And we can see that although I send the pulse in this time, by the time I get to the next sampling time, I still have some residual energy from the previous pulse, which is going to get in the way of the new one. And that is what we call intersymbol interference. We've gone over this before, so I just want to remind you about it. So we know, now let's get to this question of the choice of the waveform. We know that we should match the transmit and the receiver. Okay, that's part of it. But what do we send to begin with? What is the transmit that we should be matching with the receiver? We said it's free, but we have to be practical. So all choices are not really equivalent because some are robust to impairments and others are not. So we're going to look first, I said we're going to be talking about avoiding ISI from the channel. Avoiding ISI is our first objective. And so in order to avoid ISI, we're going to consider a family of pulses called Nyquist pulses. So the idea of using a Nyquist pulse is to avoid ISI. And as I said, there's a family, there's a large selection of them. And so within this family of good choices, which are Nyquist pulses, we're going to try and find ones that are robust against non-ideal components. And since there are several Nyquist choices, we'll find some that are good. And in fact, the first homework assignment is based on playing with these practical Nyquist pulses. So what is a Nyquist pulse? The definition of a Nyquist pulse is that it is a pulse which goes through zero at all sampling moments except t equals 0. T equals 0, I don't want to go through 0, I want to have some information there. So that means that for all, so this is the symbol time duration. And then, of course, we sample at multiples of this symbol time. So we want a pulse so that when we're not at the primary pulse where the data is, but all of the other subsequent pulses are 0. And if we respect this definition and we find a Nyquist pulse, what do we get? That means that these pulses will not contribute to ISI. That means that we can have longer pulses. Pulses may get stretched, but it will control the behavior of the overlap, and in fact will allow overlap of pulses, but such that they will not cause any problem during the sampling operation. So if we go up over here, you know, again, I could have something that stretches, but when this one stretches, it's not 0 at the sampling time. So I want to find some pulse that I'm going to allow to be wider, but even though it's wider, it will pass through 0. And intuitively, when I allow myself to have longer pulses, that means that it will occupy less bandwidth. So there are a couple examples of Nyquist pulses, and the easiest Nyquist pulse to think of is, of course, a rectangular pulse. This is, you know, 1 at the sampling time, and all other sampling times at 0s. We would actually, I'm sorry, I should maybe write this as minus t over 2 to t over 2. This is what we would actually do, and the sampling time is right here. And so at all the other sampling times, of course, the pulse is 0. So this is a nice Nyquist pulse. Another Nyquist pulse is known as the sinc function. And the sinc function has in the numerator a sinusoid. And the sinusoid is periodic. And the sine function goes through 0 periodically. And so we can arrange for this to happen at the sampling point. So this is easily meets the requirements. So periodically passes through 0. And I said that there was a family of functions that are Nyquist, and they're all related to this sinc function in some way. So we're going to be looking in particular at a choice of Nyquist pulse, and I'll be defining it in a few slides, called a raised cosine pulse, which falls in this family of Nyquist pulses. And another one very closely related that is a root raised cosine. And again, I'll be talking about this in a few slides. So square pulses, that sounds easy, this NRZ pulse. Why is that kind of problematic? Well, the problem with it is we can understand the problem in the frequency domain. So we have this pulse that you would think would not cause ISI, but what happens? You look at the frequency domain, and the rectangle in the time domain has a Fourier transform, which is a sinc function in the frequency domain. And the sinc function has a fairly wide bandwidth. Okay, certainly depending on how we define bandwidth, but it's certainly got a large bandwidth. And what that means is that it's going to be more vulnerable to a channel which has limited bandwidth. So because of this, although in theory there would be no ISI, when I get confronted with a band-limited channel, of course, this one is going to suffer a lot. And so there are a couple problems that we can identify in the frequency domain. It's kind of all saying the same thing. The bandwidth is fairly large. The roll-off is kind of slow. There's a lot of energy. The side lobes are large. And so when things go wrong with the channel, things get cut off, the impact is large. And so it's very vulnerable to intersymbol interference. So now let's look at this second choice for a Nyquist pulse, and that was called the sinc function. And I put the title of this slide as spectral efficiency because this is what's really good about this choice of Nyquist pulse. So let's look at the time domain. So in the time domain, we have a sinc function. And in the time domain, the sinc of t over t, we can see the main lobe is of width 2t, and the zeros happen at, multiples of t, so, it clearly meets the criteria of being a Nyquist pulse. And, a square pulse, would have been from minus t over 2 to t over 2, but this one goes, much larger, much greater in time. Now, if we look in the frequency domain, by duality, we know that a sinc function in the time domain is actually a rectangle in the frequency domain. And so this is, if you can think of it, it's like we've shoved all of the energy into like the narrowest bandwidth we could get. We make it rectangular, so we cut it off completely. And because of this, it is the most spectrally efficient of all of the Nyquist pulses. Nyquist pulse is a family, and among this family of all the pulses that go through zero at multiples of the sampling time, this one is the most spectrally efficient. So we call it the ideal Nyquist pulse. And why is it ideal? Well, it's ideal vis-a-vis this spectral efficiency. So it's the most spectrally efficient. And indeed, if we look in the baseband signal, the half bandwidth, of course, these are positive frequencies, and negative frequencies don't exist in reality. And so if we look at the single-sided bandwidth of this signal in baseband, the bandwidth would be 1 over 2t. So in the future, remember that I said that there were those, the famous trade-off, which was BER, spectral efficiency, and cost. And we're going to want to be balancing those. And when we compare things, we'd like to be able to have some sort of benchmark for spectral efficiency. So when we talk about modulation formats in the next weeks, we're going to be talking about the spectral efficiency of all of these different modulation formats. And we're going to compare them based on the assumption that we have used the most spectrally efficient pulse shape that we could. So when you see specifications of spectral efficiency, it will be based on the assumption of this ideal Nyquist pulse. So we want to fairly compare all of them, so we assume in the comparison that they have occupying the minimum spectrum possible. So if we think of the data rate, how many symbols per second can we transmit? Well, and that's what we know as RS, the symbol rate. The symbol rate is just the inverse of the time of a symbol. And what we're learned from this is that the minimum bandwidth, which I've said is this two-sided ideal Nyquist pulse, whose single-side bandwidth is 1 over TS. And now if I put this in terms of the data rate, that means it's 1/2 of the data rate. So that's the minimum bandwidth that we can use to transmit our information. And that means now I'm going to define something called the spectral efficiency. Finally, I've talked about it, and now we're going to define it. And it's going to be this ratio of the data rate divided by the occupied bandwidth. And again, when we're going to be comparing them, we're going to be comparing them based on the minimum occupied bandwidth. And for instance, the maximum spectral efficiency for binary signaling would be 2 symbols per second per hertz. And in particular, the maximum spectral efficiency would be 2 symbols per second per hertz, the units for spectral efficiency. Okay, so now we've talked about bit error rate floor. We've talked about, we've talked about bit error rate. We've talked about the typical waterfall curve. And this came from the Q function. For instance, for BPSK, we had this curve. And these curves, I guess we had BPSK and we had on-off keying, and we compared those. Those are the first error curves that we had to look at. And these have this typical waterfall characteristic. And this is because we assume that this is a system where the signal is not crushed by noise, that in fact we can have the transmitted signal have a matched filter and that there's no distortion introduced, and then we would have this performance. However, what happens when we have intersymbol interference? Well, we don't have this same behavior. For instance, in this behavior, as long as I can keep making my signal stronger, if I keep making my signal stronger, my probability of error keeps going down. That's what waterfall means. As long as I keep moving to stronger signals, the bit error rate goes down. So what happens in the presence of intersymbol interference? Well, now when I add more power, it doesn't help me because I'm getting self-interference. It's my own bits that are interfering with me. And so what we see is something called a bit error rate floor. That at a certain point, I increase the power of my signal and it doesn't help me. The errors are not coming from additive white Gaussian noise, which is improving with EB over N0 improving. Instead, it's coming from the self-interference, and so a very different behavior. So this is very bad. A bit error rate floor, very bad, and we want to avoid ISI so that we can avoid this behavior. So how is it that we're going to avoid ISI? So far I've talked to you about these square pulses, which look bad spectrally because the sinc function is just too wide. We looked at like these ideal pulses, these sinc pulses in the time domain, which are rectangular in the frequency domain. But we haven't talked about how practical they are. So we've talked about how spectrally efficient they are. For instance, that's the sync T over T. All of them avoid ISI, which are Nyquist. But now I'm going to talk about which ones are practical to implement, which one are robust to imperfect components. And that is where we introduce the raised cosine, which is a family in itself of Nyquist pulses. We're going to look first in the time domain at what this pulse shape looks like. First of all, I'm going to identify here, there's the sync function. So, and now we have here the cosine, and this is where we get the name raised cosine. So we're multiplying by this other term. And it looks a little funky in the time domain, but let's look at what the frequency domain looks like for this signal. And in the frequency domain, it has a very simple form. And we can see that it's a bandwidth limited pulse, has finite bandwidth, and here we see a cosine squared, and because it's squared, it's strictly positive, which is why we give it the name, the raised cosine. And you know, one thing you might have noticed is that there's the sync function. We have this factor called R, which appears in the expression, and that's what parameterizes the family of raised cosine, and it's known as the roll-off factor. And the roll-off factor determines how much bandwidth is occupied by this pulse. So if we look here, it's a function which is 0 outside a certain interval, and it's constant inside another interval. And then in between these values, it sort of rolls off. And this roll-off section is given here. So here's the part that's 1, here's the part that's 0, and in between this raised cosine gives the shape of the spectrum. And R is the parameter that determines exactly how much it rolls off. And you can see that how much bandwidth is occupied is determined by this factor R. So here are some plots of raised cosine. So this is the frequency domain, and this is the time domain. So in this family, you can see that the time domain signals, of course, they actually are infinite support. You know, they go from minus infinity to infinity, so they're not causal signals, they're not practical, but of course, we can always truncate it and approximate them. So these are, if we take the example of R equal to 0, let me back up. R equals to 0 here. I'm going to get cosine of 0, which is 1, and this is gone, so that's just 1, and I just get the sync function back. So this is a sync function, which is why when I look here at R equals 0, you know, I have a rectangle in the frequency domain. So that makes perfect sense. And now we can look at, as we change the roll-off factor, what happens. And the maximum roll-off factor is 1. R is always between 0 and 1. And at the maximum roll-off, I have sort of doubled the frequency, which is not 0. So in the ideal one, I would stop at 1 over 2t, and with this slowest roll-off, I would get twice, it would not go to 0 until 1 over t. And in between is sort of traded off. So we can think of the roll-off as sort of telling us the percentage of extra bandwidth that's occupied. So at R equal 1, it's 100% of extra bandwidth. So there's two things. We can see that using this R roll-off in the frequency domain, it's pretty clear as we're occupying more frequency. And you know, I should mention that that's the absolute frequency when it goes to 0, but if we looked at definitions of like 3 dB bandwidth, or they would all be the same, but if we looked at the definition of the amount of power concentrated in a certain bandwidth. They would all have different bandwidths. So let me now look at the time domain and what's going on as I change the roll-off factor in the time domain. Well, as I change the roll-off factor in the time domain, we can see the size of the side lobes is changing. Or we can think of it as the how quickly the time domain signal is going to 0. So I say it has infinite support, but some of them go to 0 very much faster than the other, which is like the size of the side lobe. And for the sinc function, in order to have very compact frequency, that means that I have fairly large side lobes. But as I increase the roll-off, my side lobes get smaller and smaller. And why is it important that I have small side lobes? Well, that's because of errors in timing. Suppose I sample at the wrong time. If I sample at the wrong time and the side lobe is big, I'm going to not get 0 contribution as I want to have with a Nyquist pulse. It's supposed to give 0 in intersymbol interference because I sample at the time. But if I have an error, then a big side lobe is going to give you a big error. Whereas if I have small side lobes, then even if I have timing error, so I don't have like perfectly 0, it will be quite small. And so it'll be robust to those kinds of changes. So this is a trace of a bit sequence for two different roll-offs. And I just like to show this because you can see that this function, this sequence, this data sequence, and we can see it's 1, 0, 1, 1, 0, 0, which is sent. Those are the pulses which have been transmitted. You can see that this is, it's not like a square pulse where they just stay either at the value +1 or -1. In fact, for r = 3, we can see there are large excursions, and r = 0.3, excuse me. But the important thing is when I sample, I'm getting something that looks like just the symbol that was transmitted. So that's why I can tell this is a 1, this is a 0, 1, 1, 0, 0, because there is no interference. But if I look outside of the sampling points, well, then it's hard to see what exactly is the sequence that's been transmitted. And in some cases, it's not a big deal, like for r = 1, I don't have much exceedant, and that's because the side lobes are small. But in the case of the trade-off, maybe with 0.3, which is more spectrally efficient, but there'll be more excursions and could be more subject to errors. You know, if the timing is not perfect, it would be more subject to error. So that was the raised cosine pulse. Now I'd like to talk about root raised cosine. And what does this mean, root raised cosine? Well, I'm going to define root raised cosine, first of all, just give it a definition, that it is the positive square root of the frequency response that I gave earlier. Okay, so this idea of 0, some roll off, 1, some roll off, 0, I'm going to take the square root of that, and I'm going to call that another kind of pulse. So clearly, if I square the frequency response, I'm going to, for the root raised cosine, I'm going to get the raised cosine, which is why we get the name root raised cosine. So why do I care about this? Because I said we have in a system, we're going to have the transmit pulse and the receiver is going to be matched to the transmit pulse. So if I want the overall response to be a Nyquist pulse, what I have to do is divide that Nyquist pulse between the transmitter and the receiver. And so what I'm going to do is I'm going to have my transmitter actually transmit a root raised cosine. And the root raised cosine will not be a Nyquist pulse. However, what the receiver will see is the concatenation of two root raised cosine filters, and when they come together, I get to the raised cosine. And so what the final decision process is based on is seeing the effective pulse, which is transmitted and received filters, and that will be raised cosine. So if I want to have an effective raised cosine, I'm going to use a root raised cosine at the transmitter and a root raised cosine at the receiver. This is trace for the root raised cosine, and as I mentioned, it's not actually, this is for the same sequence, I believe. It's not actually a Nyquist pulse. So at the timing instance, I'm not going through exactly plus or minus 1. I'm off. But that's because I haven't gone through the receive filter yet. And when I go through the receive filter, I will return to those 0 ISI components for this system. So it's not a Nyquist pulse. So now I'd like to go through a demo in Matlab on root raised cosine. You can do the demonstration yourself if you follow this sequence. If you go into Matlab and look at the communications toolbox demonstration, and you look at the physical subsystems, subcomponents, and you look at filtering, and then on the filtering topic you can look at raised cosine filtering. So they have a very nice tutorial where you can see them generating all these pulses. In the homework assignment, I'm not asking you to write the MATLAB. That's already done for you, but I'd like to let you know what is happening inside of the file that's being provided to you. So you could open up the source code for this demo in MATLAB, and it explains to you what's going on for this raised cosine filter. And in fact, raised cosine is a command available in the communications toolbox in root raised cosine. So for instance, you would generate random bits, then you would ask MATLAB to create an RC filter, and you would specify what the roll-off and what the delay is. I'll explain what the delay means. And then when you actually want to put your data through the filter, then you would use this function step. The command raised cosine transmit filter here, it can generate a raised cosine filter, or it can generate a root raised cosine, RRC, as well. So here are the commands where we start to talk about the delay. And, so first, before we talk about delay, we'll talk about what is the truncation that we're going to introduce for our pulse. Because I said, you know, this is not a causal pulse. It's supposed to go from minus infinity to infinity, but in order to actually have a realizable pulse, what we're going to do is we're going to truncate it. And we have the choice to truncate it, and we can choose after how many side lobes we want to truncate it. And we can choose after how many side lobes we would like to truncate it. So in this case, this is a filter with 6 symbol durations for the pulse. So if I'm going to truncate the pulse, I have to introduce a delay as well. So whenever we're doing a causal version, what are the two things we do? We truncate and we delay. That's how you make it causal. And so if we decide that we're going to have something that supports 6 intervals, then we're going to have to introduce a delay in order to have the output come out correctly. So in this case, because we chose a duration of 6, we're truncating, you know, after 2 side lobes. And the delay, of course, is going to be half of the duration, or 3 symbol intervals. Next, I'd like to talk about when we do filtering, there's a certain internal upsampling that happens inside of the filter. And it sort of gives you the resolution of the shape that you'll be creating, and that can be specified. And in here, there's a factor of 8 oversampling in this example. And so now we have 6 symbol intervals, but there are 8 samples in each one of these. And I hope that you can see as I'm changing the blue color here, I'm going through different symbol intervals. And so you can see there are 6 different symbol intervals, and with each one of those you can see we have like 8 samples. And that gives us the shape of the raised cosine filter within it. And the delay, again, we have to introduce a delay of 3 so that we have the peak of our pulse actually occurring when we want it. So this is a trace of the sequence that is generated inside of Matlab, and we can see that there's this startup time when things don't quite make sense, when I've introduced my delay for things to sort of catch up. And then we can see where the timing is of the symbols. So this is the data after filtering, and then with that delay introduced. So just as a reminder, you input something with 1 sample per symbol, and you get out something with 8 samples per symbol, because we had this oversampling. Once I do one filter in Matlab, if I do another filter, I have to tell the filter, do I have 1 sample per symbol, or do I have, like 8? So you have to tell it when you specify the filter command. And so that's what's going on in here in this filter command. So I said that inside of this command raised cosine filter, you can specify which of the Nyquist pulses you want. In particular, this does raised cosine or it does root raised cosine. And of course, you can specify the roll-off factor that you want. So this is an example of the root raised cosine pulse. And the last thing I would like to draw your attention to is the equivalence. Like, you could take 2 root raised cosine filters and it gives you an RC filter. That's certainly true. We have to add noise, and in the Matlab code, if you're interested, you can look at it. It adds noise using this command called additive white Gaussian noise. And you specify the signal to noise ratio you want, and it generates the amount of noise appropriately to achieve that SNR. Now, normally you would do this with, here's your transmit and here's your receiver. So normally when you'd have your transmit and your receiver, so here's your transmit, here's your receiver, you would add noise in between them. And as I mentioned earlier, that would have additive white Gaussian noise, which is infinite bandwidth, and the filter limits the amount of noise power, which actually is coming into play. Afterwards, we're going to plot what we call the eye diagram, which I'll be explaining. And if we plot the eye diagram, which is just a superposition of all of the symbols, we would see the effect of the noise and the pulse shaping. And in fact, that is what the homework assignment is about. I wanted to mention that you could try to make an equivalent system where you have a single filter, and this is what I alluded to at the very beginning of this lecture. And if we did not have any filter here, then you could come up with something very different if you didn't change your command. If you use the same additive white Gaussian noise command in these 2 simulations, you would get different results. And in particular, if you do it this way, you would get this nice open eye. And if you did it the other way, it would be very noisy. And that's because of the noise not being filtered. So I mentioned this. It's not important for the homework assignment because we're going to give that to you. But I mentioned it for your own future simulations where this might be, let me say, a common error. Okay, so that covers the root raised cosine pulse shaping. So we put it in the context of Nyquist shaping in general. Went specifically to root raised cosine, very practical, good trade-off, used often, very extensively. And in a homework assignment, you will be manipulating different raised cosine pulses. You will be looking at the effect of different roll-off factors. And because of that, we will be generating those pulses actually in Matlab. And so I gave you a look at a look behind the curtain, if you will, to see what's going on in the background in that homework assignment. But you're going to be essentially examining these eye diagrams and trying to figure out what happens when I do different choices for the roll-off.